Now we will solve our first problem on the design of flexible pavement by AASHTO method. In this method, we get some parameters of the soil layers in the form of modulus of elasticity. You can see it from here, that is E1, E2, E3, and we have got modulus of resilience of subgradient. And there are four layers, actually three layers. First layer is for wearing course, and this layer here is for base, and this can be said it sub base, and the underneath layer is actually subgrade in situ soil condition. We are asked to find out the value of D1, D2, and D3. These are the depth of each soil layer. In this method, first of all, we find out structural numbers, and that is based on the parameters what we have, that is the vehicle parameter, which is ESEL, equivalent single axle load. It actually says that uh, how many repetitions of an standard load, that is 18 keep, and you have reliability, and you have standard deviation. That two are for the loading, that is ESL. You have a reliability of 95%, and you have a standard deviation of 0.35. And you have some serviceability parameter, that is 2.1. What does it mean? For a road, you have initial PSI, let's say initial serviceability index initially you have. And for a fresh road, just constructed road, it might be around 4.2. And yeah, we limit that for terminal PSI. For terminal PSI, that is actually 2.2 or 2.3, something like that. And you have been provided the difference of PSI. Based on this parameters ESAL, reliability and standard deviation, and E1, E2, and E3, we will first of all find out structural number. These are first requirement. And based on structural numbers, we have a formula. Using that formula, we'll find out the value of D1, D2, and D3. So let's find out. Let's say uh, for D1, let's say we have a structural number S1, and for D2, we'll find out the structural number SN2, and for D3, depth D3, we have a structural number of SN3. And to say another thing, that is when you are actually calculating the structural number, you need a modulus of elasticity. And for that, you will consider for S1, E2, and for SN2, you will consider E3, and for SN3, you will consider MR. So when we will uh, read the graph, then you will find the uses of these things. So let's find out these things. That is SN1, SN2, and SN3. These are just the math part. I'm not going to the theory behind it. We'll just do the maths and show you the steps. I'm trying to open a graph. That is that. It's from a book named, I forgot the name. Anyway, so here you can see that you have a reliability, and you may call it a traffic line or a turning line. I asked ChatGPT and it told me it's traffic lane, but it's actually a turning line or a reference line. You have another turning or reference line, and the parameters that you need, that is these lines represent reliability, and here you have a slanted line, that is overall standard deviations is not, and you have a line that is for this is for what you can tell ESAL, and you have another parameter, and that is uh, effective roadbed soil resilient modulus, and you can see that this is actually MR, but for this math we will consider E2 and E3 as it is as MR, and the units are same, and to do the math you need not to convert this E2 in MR. Anyway, let's find out is in 1. For that, we will zoom it a little bit so you can see it properly. Well, let's draw a line. Let's say our reliability was 95%. So here you can see that this is 90, and this is 99, and this is 99.9, and typically for maths in exam the reliability will be within 95%. So this point is pretty important point for you in to the maths, at least for uh, pavement design. And we have a standard deviation of 0.35, and then this is that point, and let's mark a little bit. So you have this point over here, and you have this point over here. Oh, it's black, can't see. So you have this point over here, this point over here, and you have an ESAL value of 18.6. So it's 10, and it's 20, it's 30, it's 40, it's 50. So it's 15. So 18.6 will be somewhere, let's say it's 15, and 18.6, it will be and half of the distance. So it might be here. So now we'll construct the line. Let's and to zoom it a little bit more for accurate measurement. Well, this line, okay, so far so good. And now, and sorry, my computer is lagging, give me some time. Okay. Okay, now we'll join ESAL value. Now you can see that we'll join this, and we'll extend it to the up to the turning line, and for that I will bring it again, and you have a point over here, and it will go like this. Did I made any mistake? It should, I did it before, it will match the point. Well, I said the point is right here, and it's 1805, and for that we'll extend it for, where it's not working, shitty piece. Control minus. Well, now we'll extend it for effective roadbed soil, and we'll consider E2 to find out SN1. And for that, we'll join this line with, let's say, that was, if I'm not wrong, that was 30. So it's 20 and it's 25 and it's 30. If I'm not wrong. Yeah, it's 30. So for that, the line would be somewhere over here. Well, now what you will do, we'll extend it. We'll extend it, but up to what point? We'll extend it for del psi. You can see that this is for this one is for this line, this 0.05 is for this line, this 1.5, this is 2. So in our case, del psi was around, if I'm not wrong, it was 2 point something, 2.1. So these lines are so closely spaced, so it would be fine if I zoom that. But if I zoom, my PC doesn't work. What kind of shitty behavior? Well, now I will join this line with, let's say, the 2.1 point was this something, fine. And then from there, I'll extend it like this. Let's say the point is somewhere over here. And let's say the value is, let's say our SN1 is 3.2. I'm writing is 3.2 because I calculated that before and it was 3.2. So you may call it 3.1 or 3.15 or something like that, but let's call it 3.2. Well, we need to find out SN2. For SN2, we'll consider E3 and everything will remain same as it was before. So we'll just connect this line. We'll just connect this line with, and our value was 11,000 if I'm not wrong, and is 5, it is 10, and 1100 will be sorry, 11,000 will be somewhere over here, maybe. It would be fine if I zoom it a little bit. Okay, pretty fine. Now we'll extend it. To extend it, we'll go as we went before, unless the point is somewhere over here. Oh God. Well, it should be actually 4.5. I did it before. I'm showing that again for you. And for this piece's work, I'm lagging. Okay, let's see. This is that point, and let's say SN2 is SN2 is 4.5, and the later part is you will pivot at this point, and you will go it for the MR value of subgrade, and it was what, it was 5700. So 5700 would be somewhere over let's over here. And if you connect this, if you connect it like this, and then extend it like this, and then you can get the value like this, and let's say the value is Sn3 is 5.5. So this is how you can find out the value of Sn. So you have Sn1 3.2, Sn2 4.5, and Sn3 5.5. So let's go back to the problem. Well, now you have Sn1 3.2, Sn2 4.5, and Sn3 5.5. Now the question is, how can you find out the depth? So which is our main target? So you have an equation that is Sn is equals to A1 D1 A2 D2, and you have a coefficient that is M2, and you have A3 D3 and M3. Now the interesting part is, what do we mean by M2 and M3? These are drainage coefficient. If the drainage is really good, the coefficient is 1.2, and in our case, the in the site condition, the drainage condition was really okay, and it's really fine. So the coefficient 1.2, and if the drainage condition is really bad, then the coefficient would be 0.4. And there are some specifications like drainage time, retention time. So based on these things, you can get drainage coefficients. So in our case, these things are given. Now the thing is, what is A1, A2, and A3? To find out A2 and A3, you have an equation that totally depend on the modulus of elasticity is E. And for A1, you have a chart, that is A1 versus MR chart, and from that you can get A3. Uh, you can say that A1, A2, A3, these things are dependent on E values, or the soil parameters. Well, in our case, these things are given, so you need not to calculate that, but you can calculate it. The formulas at PT is, let's say for A2, the formula was 0.249 multiplied by log of E2, and the thing is subtracted by 0.927. So the formulas are easy. Yeah. If in exams these things are not given, you'll be given the formula. Well, now the thing is, how can you find out D1, D2, and D3? For that, uh, you have these equations. So, when you will find out D1, let's say D1, you are finding these depths. So, for that, you will not consider the lower depths. But when you find out D2, you'll consider D1. When you're finding D3, you'll consider D1 and D3. What do we mean by that? Let's say I want to find out SN1. For that, I will just use the formula A1, D1. And from there, I can find out D1. What is that? I will divide SN1 by A1. In my case, SN1 is 3.2 and A1 is 0.42. From that, I can get a value of D1, which is I calculated before, that is 7.6 centimeter, and it is suggested that you will up around it by 0.5 inch. So I can up around it with 8 inch. So now you want to find out SN2. How can you do it? For SN2, you will not consider the third term, which is A3, D3, and M3. To find out SN2, this would be the SN2, and you will subtract. I'll not actually find out SN2. Okay, fine. Let's say SN2. For that, I will consider A1, D1 plus A2, D2, and M2. But my goal is to find out D2. So for that, I'll keep everything on right hand side. So for that, I will get SN2 minus A1, D1, and these things will be divided by A2, D2. So it doesn't look like D2. D2. So your SN2 were you don't you know it, which is 4.5. We got that from graph, and A1 is 0.42, and D1 is we upper rounded it by 8 inch, and your A2 is in this math that is 0.14, and D2 what it don't know, it don't get the D2, it will be M2. It will be M2. Our M2 was 1.2. Well, the value would be 6.8 inch. You will upper round it by 7 inch. So the same way you can find out D3. You will consider all the terms and you will get an equation uh, like Sn3 minus A1 D1 minus A2 D2 M2. And in lower you have A3 M3. I'm not putting all the values. You have SN3 of 5.5, A1 of uh, 0.42, D1 of something. You know all the values, and you will get a value of D3 in this math. Well, I'm writing that A1 is 0.42, D1 is 8, and A2 is 0.14, D2 is 7, and M2 is 1.2. And you will divide everything by A3, which is 0.08, multiplied by M2, which is 1.2, and you will get a value of 8.1 inch. You can use it, you sorry, not 8.1, you will get 11.1, 11.1, and you will up around it by, let's say, 11.5. So this is how you do the math. The math is pretty simple. You're solving this math using empirical formulas, and the main thing is Sn. For each layer, you find out Sn using chart, and for the depth, you consider each term, and you can find out the depth. Well, you have some uh, minimum requirement of depth, which is based on ESAL. You can check that, and you should check this. And for my case, everything passed. Normally, it passes for high loading, maybe. So there's a chart for that. So this is the math. We'll solve rigid pavement soon.